guys, you scared me. What are you doing here in southern Ontario? Oh, me? Well, I was just thinking about legacy sediment and how legacy sediment kind of depresses me. Because down here on the Credit River, this is my getaway from the things of humankind. At least I try to. Get away once a day, bring the dog, let her walk around. Yesterday it was freaking snowing. And when I think about legacy sediment, I realize, gosh, even when I try hard to get out of the house and get away from the hum of the highway and find a place that's most natural and always streamside, just because I like it the best, I'm confronted with the fact that the footprints of human behavior are pretty much everywhere because we live in the Anthropocene. So when you are learning about legacy sediments, I want you to, you could also call them Anthropocene sediments or sediments of the Anthropocene, which means in recognition of this crazy period where one species has taken over and exerted a dominant force on most of the geophysical systems and geochemical systems. Basically, you can see us in the ice sheets, you can see us at the bottom of the ocean, you can also see us on the river channels, like this one. And I'd like you to go and look for this phenomenon in a nearby stream, hopefully the one that you've been working on for the last few weeks. And I've posted an article which is by a good friend James, who Professor James won the Grove Carl Gilbert Award just before my advisors did in college, and I have a great admiration for this scholar. And what this publication is really getting at is that most of our streams that we try to understand, we got Bankful, like you've seen, you can read a Woolman pebble count. He said, wait a second, we have a lasting legacy of the Anthropocene that began at least 150, if not 200 years ago. And you can't really understand the evolution of a stream without factoring this in. They're not all perfectly sort of virgin or native systems that haven't been impacted by humankind's crazy land use behaviors. And even though this stream, wow, Mira's got somebody's shirt or something. Even though the system looks pretty much natural, okay, there's a highway in the background, this whole mound where Mira found the trash is all legacy sediment, for sure. And this is a product of our sort of early industrial past. Up here in Canada, and also down in the Northeast and the Mid-Atlantic and definitely the South, before gas and coal and nuclear, people still needed to run light industry, needed to have sawmills and grist mills to grind grain. And the number one source of power to do this work, besides I guess donkeys and poor unlucky dogs, was to dam up a river and then squirt a little bit through in a sluice, or let it roll over a water wheel. And you might think, okay, wow, that doesn't seem like that big of a deal. But if you think of pretty much every stream that you can think of, in the Georges Creek included, at some point in its system it had a major dam, or even a series of smaller dams. And when they were put in was also a time of landscape clearance. And this forest is probably no more than 100 years old. And if I look out there, the stem diameter beyond Mira in this basically giant legacy plug is probably 70 years max. So this is the stuff. This is the legacy sediment that James is talking about in this evolution. And what I'd like you to do is to travel to a nearby stream after reading this article and take a walk. And you're going to be looking for things that are incongruous, where you know the usual flow pattern and how much material can be transported by a system, and look for things like this big bar. This big bar is not full of a diversity of grain sizes. It's full of a pretty singular grain size. There are some smaller clasts, but notice what's missing on this turn, on this slip bar. And I'll go ahead and answer it for you. It's sand. It's sand or silt or clay, and the bulk of this material is this really difficult stuff to push. And you can see this is a pretty large clast, and it takes a lot of velocity to move it. And yes, it did move it up to this point, but it's having trouble moving it beyond, just out to Lake Ontario. And it adheres to this model that James produced, and this is a chart from the article. So here's a normal system, and then let's say you let a whole bunch of humans come in, and they really love maple syrup and hunting beavers and making farms, and they chop down the forest and build cabins, and then the sediment fills up the stream valleys. And this is that initial pulse of legacy material. So natural stream, and then a whole bunch of sediment comes in and fills it. And then the legacy part is your stream is evolving after that. It's still compensating for this original early industrialization clear-cutting phenomenon that happened pretty much all over the east coast of America and also here in Canada. And if you come out to a system, let's say today, you're still seeing the impact. Like we look at bankful levels and we see only this, and we're trying to understand the evolution of our system. And it's really hard to do if we haven't factored in this earlier history where the system isn't just carte blanche. It hasn't just been doing its sediment delivery system since you were born, or it's not by design ready to teach you hydrology. It's still dealing with, I guess you would say, some trauma from the past. And bless you, Mira. And on this sheet, this is also a chart from James. He's outlining where sediment, as you proceed down the system, is usually trapped. And you have gullying. This is, he's saying, the source of your sediment, and this is colluvial material and alluvial material. And he's just basically telling us throughout the system you'll see a different mix of grain sizes from source to sink. And a lot of earlier hydrologists and geomorphologists thought, you know, you erode it here and you'll see it down here eventually. And that's pretty linear. And that's unfortunately not the way it works. How it works is there's a dynamic force of things get clogged here and stuck way up here, and then years later the stream has enough power to move it because of some other land disturbance, and it does. And here's another way to look at it. This is also from James's article, and you can see here is a system in perfect equilibrium. It's sediment delivery, DS, D sub S, and transport capacity, TC, is equal. So basically the stream has enough energy to transport the material that it has to transport. Okay, that means basically not this system. And what we're looking at this time is, you can see the sediment it needs to deliver, like what Mira is standing on, is much greater than its transport capacity. So the sediment it needs to deliver, like these big clasts, is greater than the sediment or the stream flow to actually make the material move. And another type of situation you might see is the opposite, where you have a high transport capacity, the potential to move material, but very low sediment to deliver. And what that usually equals is highly incised streams. So when you're out and you're trying to, like, okay, I gotta find an area that's been impacted by humans and how it's been expressed in a stream. And it could be like B in this scenario, where sediment delivery is way outstripping the capacity of the Credit River here to deliver it. And you can see it because even though this thing's humming along, look at this chunk. It's only during the highest flows that it can actually push this through. And you could find yourself on another system, and I'm expecting some of you will, and it might look a lot like scenario C, where you have high transport capacity and low sediment delivery. And what that's going to look like is, what I'm guessing is pretty much really clear streams. If any of you are left, I know some of you are left in Western Maryland, and there you have steep slopes and usually pretty high capacity compared to the class that it needs to take. I know some of you from your earlier assignments have given me things where you're looking at systems that are choked full of mud, and the system might not look like this at all. It might look like instead of large class, you don't have a single stone, but you might still be in a system that is choked with sediment and doesn't have the capacity to transport. So in other words, just imagine this away as rocks, and instead fill it in with mud, sand and silt and clay. And that would still represent the same phenomena, that you have a stream system that would like to transport it, but it cannot, and it's out of whack. And where did that sediment come from? And you know, what does that tell us about the health and evolution of our nearby streams? And it gets really fun when we think of legacy sediments in terms of stream restoration. And that's sort of the last component of our class is, you know, what are we restoring for? And are you aiming for, you know, just to bring some fish back and to put some bugs back and maybe some cute doggies, and then that's the end of your job? Or are you looking to rebuild a total ecosystem, or even make it function like it originally should and is supposed to? And that's what's really fun. And also, it's just, I find a great deal of joy just being able to read a system. And I can, from this vantage point, I can read the whole watershed. I can tell that this system's out of whack. I'm just here on this one part of the reach, and I can see that it's having a hell of a time transporting all this material. And then the type of material it can transport, it's eroding and taking away, like the smaller class, that all that silt and clay and sand that's stuck there on that bank, and then it's been protected by that riprap up there. That's human introduction. And then you can see they're just trying to protect the sediment sizes that the river does have the capacity to transport. So it's eroding and moving the stuff that people don't want, because it's going to erode away the whole forest. And part of the reason is because of this legacy of previously eroded sediment that the system is still trying to transport, and it can't, so the system's moving over there and trying to erode that side. And it's all just telling the story that all through here, people have not only trimmed down trees, they've also blocked part of the system and created these big plugs, like this big bar that I'm standing on, that the sediment is basically suspended and stuck within the system. And that's basically it. I'd like you to read James, take a look at these diagrams. I'm pretty sure most of you will be in scenario B, and you'll have a stream that can't quite transport the sediment that it needs to. And then our last portion of the class, we're going to look at restoration and what it means for bay health. And I have a video